All right, so these are the different features that I left off in the last video concerning the Milky Way galaxy. So remember the three main parts: the disk, the halo, and the nuclear bulge or the galactic bulge. All right, so the disk, relatively flat. It has a mixture of old and young stars. I'm pointing out some of the things that are really important. Obviously, the whole table is important, but these are more important, I feel. So the fact is that the disk contains gas and dust. Right. So the new stars can still form. You got to have the gas and dust for that to happen. Notice the difference with the halo, right? The halo is spherical. All right, it goes around the disk and also around the bulge. It is slightly flat on the top and the bottom, but more or less spherical. It contains very old stars, so more than 10 billion years old, and we find no gas and dust, absolutely no gas and dust, and there's no new star formation. There hasn't been since 10 billion years ago. The orientation. So the thing about the disk, all the stars are moving around the disk in the same direction, just like the sun. But with the halo, let's take a quick look at the halo. You got things that are going in all sorts of directions in different orientations, right? Whereas on the disk, everything's moving in the same direction. All right. What else? That's not as important. The bulge is more kind of a football shape, as I mentioned in the last. It contains a mixture of old and young stars. And by the way, the reason that there's the older stars is because the galactic bulge, things are more mixed up. We feel that there are some of the globular clusters can be passing through the bulge, right? And some of the globular clusters can even be passing through the disk of the galaxy, of course, in their orbits. So anyhow, so you get this mixture. There's still gas and dust, so there's still star formation taking place. And the thing about it, within the disk, there's also this random orientation, right? In this spherical region, you've got stars going in all sorts of crazy directions. Especially when we look, or when we use radio and infrared images of the supermassive black hole, and we for example, when we look at that. We can get stars in different orientations going around around the supermassive black hole at the center. All right, so this is a brief understanding or trying to understand the formation of our galaxy. We think it started very similar to the way we have stellar formation taking place. These huge clouds of primarily hydrogen and helium that, so you're talking about almost 13 billion years ago, that had primarily hydrogen and helium that comes from the Big Bang itself. And these things, these smaller spheres will join together, and there's star formation taking place because there's a collapse, a gravitational collapse, and so therefore you get star formation, and then these things will gravitationally merge towards each other, and you'll get in this part we actually understand quite well. Once you get an overall rotation taking place, then due to angular momentum, the conservation of angular momentum, this thing, whatever its original shape was, will flatten out. It flattens out quite nicely, and you have the formation of a spiral galaxy. All right. Let's see, measurement of the position and motions of the spiral. Okay, so this is just, there's where the sun is. This is an artist's rendition. Just keep in mind, like the spiral galaxy, or our galaxy, not the other spirals have different sizes, but ours has a diameter approximately of 30,000 parsecs, 30 kiloparsecs. All right, and we're not entirely sure of the edges, where the edges stop on our galaxy, but they seem to be about 30. It seems to be about 30,000 parsecs across, and you can see in this artist's rendition, there's the small and large clouds of Magellan, which are two satellite galaxies. All right, anyhow, the spiral arms, the thing about our galaxy is the spiral arms don't rotate as a single object, right? They the way like a record player, that's a solid object that's rotating, or a disc, if you remember CDs, they rotate it as a solid object, whereas the spiral galaxy, the arms are spinning at what we would say differential rotation. They're rotating at different rates, and so because of that, right? Because of that physical phenomena that we can measure the speed at which things are rotating, and we can figure record those different values, different distances from the center of the galaxy. It turns out, just due to the physics of this rotation of these spiral arms, we feel that the spiral arms would wind up. They basically wouldn't show any spiral structure at all after just one or two rotations. But of course, we look out into the galaxy, into other galaxies, and we see spiral arms, as far back into the universe as we can see, and so there's no particular time when the spiral arms do wind up, and you don't see spirals, and so we feel that there must be something that is causing the spiral arms to spiral. All right, and now it's a bit of a mystery, to be quite honest with you. It's still a bit of a mystery, but one thing that we have proposed, and this still needs to be proven, but it works really well, is what's called these spiral density waves. Right, a density wave, for example, the sound is a good example of a density wave. So sound is what sound is doing. Like, you just think about sound in the air. You're compressing the air and then stretching the air, compressing and stretching, and that's essentially, that propagates or moves the sound along. The air molecules don't really go anywhere, but they get squeezed and then they get stretched, squeezed and stretched, and that squeezing and stretching just propagates along with these things. Now, and water is the same way, right? The water molecules are, in the ocean or whatever, are moving up and down. But the wave is moving. The wave moves perpendicular to that, and the individual water molecules, they'll move up and down a little bit, but they're not moving along with the wave front, right? The wave front is just that's the energy that's moving along, right? And so to resolve this problem of the spiral arms just kind of wrapping themselves up at some period in history, and not displaying spiral arms anymore, there's very strong evidence that the spiral structure has been around for since the time of the formation of the Milky Way, and so to maintain that, we've come up with this idea of what are called spiral density waves, and so a density, as I said, the density wave is is very similar to sound, and it's not sound at all. Okay, but what happens is these density waves, which are generated at the center of the galaxy, propagate outward, and where like if you think about a wave, right, it crests, and then there's a trough, the lowest part of the wave. So the highest part of the wave and the lowest part of the wave. Where the highest part of the wave is where you see the spiral arms. So that's the basic idea. All right, now, so let's take a look at this. Let's see. So and there's a second idea as well. Let's see. Yeah, here we'll go back to that. The problem with this, I mean, there is certainly a problem with this spiral density model, is we don't have a way of, when we don't understand how the center of the galaxy, the central bulge, can generate a spiral density wave. It would be really nice to have a mechanism that generates this, but if there is something that generates the spiral density wave, that would maintain the spiral shape. All right, so they're showing us, so as a cloud of dust moves through the spiral arms, an increase in density triggers star formation. This may continue to it may contribute to propagation of the arms, and like I said, how that happened, we don't really understand. So here's another example of a wave, where it's a density wave. Like, if you ever pass, a traffic accident and the cars slow down, so that's an increase in density. And then, as you pass the accident, you get far away from, if there's any police cars or whatever, it spreads out, right? It thins out. All right. So that's an example of a density wave. All right. So, yeah. All right, so orbital speed depends on the amount of. Okay, yeah. So for that, when we can look out into the not in the visible part of the spectrum, but we can look out into the disk of the galaxy, and usually using radio waves and radio waves and infrared waves. And we can measure the speed. Okay, so this is called the rotation curve. And with this, we made a great discovery. It actually started with kind of an obscure observation by this kind of odd astronomer named Zwicky in the 1930s. I think he worked for Caltech. Anyhow, in the 1970s, this was better observed, and so here's what, and in fact, this was observed by a lady named Vera Rubin in the 1970s, and what she discovered was very significant. It's basically the discovery of dark matter, which again had been hinted at in the 1930s, that where it had to do with the motion of galactic clusters, but not a lot of people paid any attention to that back in the 1930s. But this, looking at like if you think about the mass of the galaxy, right? The stuff that's emitting light is, pretty much, we thought was everything you could see. And when you look out and you do a statistical analysis on the stars, and the stars seem to get, there's less and less stars the closer you get to the edges of the galaxy, and so we felt that according to Newtonian mechanics, basic our understanding of gravity is that the speed of the stars. So this axis is speed, this axis is distance. Should taper off, but it's completely not. This was not expected. This is what Vera Rubin had discovered, is that even at the edges of the galaxy, the speed of the stars is the same, and so there must be something out there in the halo that's causing this this speed that is almost flat and even increases a little bit as you get